We just introduced those micro explosion behavior by considering the water and oil emulsions. Especially, we introduced two groups of WO slurry. And the first one, we use the lower boiling point liquid fuel mixed with water as an example. The other group is the high volatile materials liquid fuel mixed with water as a second group. From the experiment on the first group, as you know, the whole the burning will be ended by the extinction of diffusion flame at the end of the droplet lifetime, because you have more water left on the surface of a liquid, and this causes the flame extinction. And the second group, you will find out you will have a so-called micro explosion occurs at the end of the droplet lifetime. Represents there is some water accumulated inside of the liquid droplet interior, and they evaporate and be superheat and then produce the high pressure to break the whole droplet into a small tiny droplets. Okay, and now I want to give you some detailed observation on the development of microexplosion for specific droplets. Basically, is water mixed with the oil. And in this case, oil basically is a less refined liquid fuel. That means that they have a higher boiling point and also may have a certain amount of impurity. And we can see in the process of the burning of the heating process of the heating on the droplets, you can find out they go through the from A, B, C, D, E, F, G, different kinds of features on the droplet size of droplet variations. And you can see starting from A, this A represents initially you may have a very nice spherical droplet. And when you bring this droplet into this experiment, actually was executed by using the two heating plates, as I mentioned earlier. There's a simple experiment apparatus. You just move your sample droplet into the region between the two hot plates. And you can see initially they just receive the heat because the outside energy will transfer into your droplet for the heating. And the first step from A to B, you can see the expansion of your droplet, as you can see the first pictures. And when you go to the next step, C step, actually they show different kinds of characters. Sometimes, for example, the upper one, they will tell you the green region represent that they have some water coming out, and you can see in the outer region, since the boiling point for the water is relatively small, then they can be easily to be start to evaporate. Then you can see they produce the several the water vapor coming out, but they still can have some droplet impinging out. Okay, there's some kinds of injection. For example, here you can see there's some kinds of micro explosion. This is one kind of micro explosion. Since you have a small region of your gas vapor produced, and they will impinge out by itself. Okay, then you can see a small droplet coming out. And since there's the whole mixing is not homogeneously, the bubble of your water, that means the water vapor will occurs in different locations. You have so many bubble exist. Those bubble, they can penetrate through the boundary of your droplet, and the whole size of your droplet will become smaller if you impinge out some of the vapor coming out. Then we call this as injection. Injection means that they were just a single bubble coming out. Okay, and then later on you will find out those kinds of bubbling become more severe and more intense, and therefore they just like a shape C. In this case, actually, the surface burning occurs for the chalk formation. And surprisingly, because I mentioned this field is quite different from the regular oil we use, because they are less refined. That means that they mix a certain amount of very high boiling point materials, and even they have some impurity. In this sense, actually, they have a found we found very interesting behavior in the final state. They have some ignition, and you can see the structure depth after the ignition. They have some kinds of fiber features at the end of the burning. Then you can see now finally, because the most of the carbon and hydrogen materials can be burned completely, then extinction, then still something left. Those material cannot be burned in the process. This is a typical burning of the less volatile, less refined fuels mixed with water, and you can see there's different kinds of micro exploring characters. And I give you another example to tell you the real applications, especially for our industry applications. Okay, you can see there is a experiment result from our laboratory study. Especially, we used a big furnace, and those furnace has a heat output is 300 kilowatt. It's not the big furnace, but is the scale is quite similar to the small scale for the industrial applications. And now we try to give you a comparison. If you use the regular fuel oil compared with the fuel oil with a certain amount of water oil emulsions, and we try to run the experiments with the same conditions, and to see the comparison between the combustion characteristics and also the emissions for these two kinds of fuel. In the experiments, there is the open symbols to represent the regular fuel oil we use in this furnace, and the black symbols represent the the water oil emulsions. In this case, actually, water is 30%. Actually, 30% is a too much percentage in most literature. They mention the the optimal percentage of oil, the water used for the WO emulsion is up to 20%. But since this is the this water oil emulsion provided by the company, they suggest they like to test the 30% water in water oil emulsions, and we try to do the experiment as the company request. Okay, let me see. There is the pictures tell you in our furnace test. We can see those kinds of micro explosion occur by using the suspended droplet, and we can see this as a micro explosion is quite strong. It impinge out the several water streams. Okay, in the heating process. Now, based on our understanding on application of these kinds of water oil emulsions, then we bring those fuels into our furnace for testing. And the first one I want to mention here in the middle, the figure tell you we run the furnace application almost 4 hours continuously after the preheating of your furnace. Actually, furnace initially is cold. We need to use the diesel oil to preheat it to a certain temperature. Being steady, then we will apply our test fuel into furnace. That means that after preheating, we start from 0, then we will have 4 hours of steady burning to see the temperature distribution, the temperature variation on the furnace. We do measurement on different locations of the temperature. R6, R7. Okay, R6 is a relative is away from the spray injections a little bit downstream, and R8. No, I'm sorry. R6 is very close to the injection point. That means that they start to inject the spray fin. Spray fin, the temperature is not too much, but at R7, actually, they are go to the main combustion region. The temperature will go to the highest temperature positions. Then they will reduce R7 continuously up to the diamond. The diamond symbol represent the temperature for the flue gas emission out. Okay, emitted out. And there is the star symbol represent the efficiency we estimate based on the excess oxygen we have in a downstream region. Okay, I want to tell you the experiment result. The first point is you can see in the period of 4 hours steady burning, actually all the temperature remain constant. That do not change with respect to the time. That means for this furnace, actually the application of the fuel oil and water oil emulsions, they will show you the steady burning for both cases. Okay, since the whole temperature distributions remain the same as in this 4-hour application operations. And now the next step I want to tell you, you compare the 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 set of the temperature variation on water oil emissions is expressed by the black symbols, including the triangle, square, and the spherical diamond. And here you can see compare with those the temperature variation for fuel oil represented by open symbols. You will see the fuel oil, the set of the temperature variation for fuel oil, they are all higher than that and than those for the water oil emission, which means that inside your combustion chamber, actually the fuel oil burning will give you the more higher concentration distribution, but for the application of water oil emission, actually they will provide a lower temperature distribution. This is a second comparison you need to know. Then the third one, actually, you find out they just opposite influence on the efficiency. You can see look at the star symbols for efficiency. You can see the water oil emission has a higher its thermal efficiency compared with the that for the fuel oil. As I mentioned earlier, when you add a certain amount of water in mixed with the fuel, actually water will absorb heat, okay, absorb heat and reduce the temperature distribution in the combustion chamber. But since there is some micro explosion occurs, that means that you will redistribute your large droplet to many tiny droplets to improve overall combustion behavior. That means that you will improve the combustion efficiency. Therefore, when you measure at the final points near the exhaust, you will find out they have less oxygen left. That means that you use the most of oxygen without too much oxygen will be emit out. Then thermal efficiency basically is higher. And those kinds of lower excess oxygen can be built from the concentration measurement in for the emissions. You can see the variation on different kinds of species in the flue gas as we measure and show in the right hand side. Here you can see along the 4 hours emissions actually for both of the fuels, for both fuels, the CO emission maintains equal to 0. That means that after the burning in the furnace, they finish all the combustions and all the carbon monoxide emission remains equal to 0. And you can see very interesting thing here for the water with oil emulsions burning. You can see the black symbol represents they have a smaller, you can see they have a smaller value for NOx emission. Okay, this is shown by diamond symbols, and they have a smaller SOx. Okay, they have a smaller SOx emissions compared with the burning of the fuel oil without water addition. And for the carbon dioxide, and usually the carbon dioxide is reduced. This is simply to be explained as this, as that since you add water into your combustion chambers, actually the overall quantity of the SOx contents and carbon dioxide, and they will be reduced because the fuel, the overall you use fuel is reduced. Okay. However, the NOx emissions is tremendously reduced from the 300 ppm to the almost 150. Is half reductions for the NOx emission, and this is the basic good advantage for us to use the water mixed with the less refined fuel oil to have a lower temperature distribution. Then will reduce the thermal NOx emissions. Okay, this is a typical experimental result to tell you by using water mixed with the fuel, especially we use the water oil emissions, then they will give you some advantage. The first one, you will increase the combustion efficiency first. Then the second, you will reduce the NOx emission. The former, the the increase on the thermal efficiency basically caused by the micro explosion to produce a tiny droplet to improve the mixing and also improve the combustion efficiency. And the reductions on NOx emission basically coming from the influence of water, because they will make the temperature decrease and make the temperature lower, overall temperature lower than 2000 K expected for the thermal NOx occurrence. Now we go back to our slides to give you some additional description on the application of water slurry. Okay, let me change screens to the slides. Okay, I hope you can see the slides. Okay, it is clear, and this slide is shown in the, let me see, is page 2.14a. Okay, and here this result coming from the literature that tell you water oil emissions can lower particulates and the thermal NOx while simultaneously reduce the excess air requirement. Actually, this sentence was approved by our experimental observation and measurement, as I described in the previous slides. And now I want to tell you there is another experiment, but they use the engine. They use gasoline engine combustor. Okay, this is a Edison T60 third gas turbine combustor, and in the left figure, they represent different kinds of water concentration by using 0% represent this is a pure fuel you used, and 5% additions, 10% additions, and since they need to add some chemical surfactants, and they don't want to show you how much percentage of the surfactants will give you the influence on the burning or on the results. And the left-hand side represent the measure the particulate concentration. The right-hand side they show you the reduction in radiation. Actually, both of them represent the same thing, because when you have a particulate, as I mentioned, if you have more particulate exist in your flame, then the flame color will become yellowish, and the yellowish color will give you the some thermal radiation outcome. Okay, the left-hand side tell you how much particulate you may produce by different kinds of fuel, and the right-hand side tell you the reduction on radiation. Let me explain a little bit here. Let's start from the left figure. They tell you the products on the particulate concentration. Okay, if sufficient concentration equal to 0, that means that they are purely burning the fuel, the test fuel, and they show you the initial particular concentration around horizontal, a vertical axis here. But by increasing the water concentrations from 0 to 5, the results shown by the square symbols, you can see as you increase the surfactant concentrations, then the 5% water addition will give you the possibility to reduce the particulate concentration. This is a reasonable expect, right? Because now if you have some water added into your liquid fuel, that will have a certain degree of micro explosion occur to improve combustion efficiency, and particulate concentration will be reduced. Okay, and this curve tell you the trend is when you increase the surfactant concentration as much as possible, actually they do not give you the too much change for the particulate concentration reductions. That means that you just add maybe 2 or 3% surfactant content is good enough without since if you have more surfactant, actually they do not give you the more contributions to the particulate concentration reductions. Okay, this is the result for the adding 5% water mixed with the original fuel. But when you increase the water up to the 10%, and you can see this curve is much lower than the previous one for the 5% water. And definitely they tell you this is if you have more water coming in, the micro explosion may be intensified by the water additions, and this tell you the influence coming from the micro explosion. Okay. Those reduction on particular concentration actually attribute to the addition of water, and the same behavior can be viewed from the result in the right figure. And here they tell you originally the reference is equal to 0. That means the reduction in radiation equal to 0. This is the reference point. And when you add the 5% of water, then you can see the jump very large, jump to the 10% reduction in radiation here as you for different kinds of surfactant concentration. Okay, and this reflects this kinds of reduction in radiation actually coming from the reduction of the particular concentration. Also, for 10% water show you the same result. They can have a more reduction in radiation. That means the yellowish color is reduced. Okay, but in their experiment, they mentioned there is a slight improvement and a degradations in efficiency on the basis of oil consumption. Definitely, because in the case when you add water in, then you will reduce a certain oil, and those kinds of water will absorb heat. For the overall power supply, power output, you will find out you need to add more oil into, and oil consumption oil consumption may be increased, and there is depends on different kinds of state and type of combustor, and test procedures. Actually, those kinds of influence coming from the water. Micro exposure is good for the mixings, but you will figure out the main additions for the micro exposure basically coming from the air. Air is inert for combustions, and they will absorb heat from the overall heat balance. Then you will you realize you cannot add water too much. if you add water too much, exceeds our experience. Usually in the literature, people always mention 20% of water added mixed with water is the maximum percentage. If you add more, then you will find out there's some degradations and not you may the whole energy output will be suffered by those kinds of water addition. But in our previous case, because the company they tell us try to do the 30% water addition, but surprisingly they do a very good job. And but this is a exceptional case, and people usually, from our experience, don't add water too much, about 20%. The final application for the multi-component droplets, we call this the coal-oil mixture, COM. And the coal-oil mixtures refer to the coal utilization. For coal, generally, we have three kinds of application for industry furnace. The normal one, actually, we grant the coal as the pulverized coal. Since you have so many tiny coal particles, then they will use the water, they use the air to blow in, and they can burn the individual coal particles. And this is a normal application for industry furnace. And recently, people try to reduce the carbon dioxide emissions. Then they try to use a so-called coal gasification. They make the coal gasified to becomes a mixture of carbon monoxide and hydrogen. Then use these gaseous mixtures as the fuel into your furnace. Okay, and those kinds of impurity, for example, the sacks or nuts will be catch in before they they go out of the gasifier. Then they will catch those kinds of pollutants in earlier before they burn the mixtures. This is another application we say coal gasification. And this is the third one, but usually it's not too much people use it. We say we use the coal, the coal particle mixed with oil. When coal particle mixed with oil, that means that they become a slurry, right? Become a slurry. Then they say they tell you the application is there's three major features. The first one, there is a direct substitution of oil by coal. Okay, then they require the crushing and the mixing process. Okay, in its preparation, but for the mixing of the oil and coal particle, actually is a more economical than the energy expensive codification and the gasification process. Therefore, people sometimes they try to use those kinds of mixing of the coal particle with oil, and they just try look at is the slurry they can pump in, pump those kinds of slurry into your combustion chamber. Okay. The third feature, the mixture is still pumpable and hence can be really used in conventional oil-fired combustor. Now let's look at if you burning coal particle mixed with oil, what will happen? And you can see this is the results for the burning of a carbon slurry droplets, okay, in a turbulent frame. And the horizontal axis represent the time variation in the process of burning, and the vertical axis and the left-hand side represent the particle diameter, right-hand side represent the particle temperature. Later on, if we have a chance, I want to tell you the carbon particle burning with respect time. It is very different compared with the burning features for a liquid droplet. The burning of a liquid droplet is described by a d-square law, right? That means the surface area is linearly proportional to the time. Okay. As you increase the time, inverse proportional, inverse linearly proportional to the time. As you increase the time, the surface area is linear decreased, okay, for the droplets of liquid fuel. But for the carbon particle, actually, you can see the diameter of your carbon particle is linearly decreased along the time increase. Okay. Now look at the whole period for the burning of a carbon slurry. You can see when you start ignite it, the temperatures for the triangle symbol represent the temperature and the spherical represent the diameter. You can see initially the diameter of this carbon slurry droplet is around 1200 micron. Okay, this is the size, and the temperature is around 400 K. Okay, temperature initially is low, but when you ignite it, you can see at first you can see here. Okay, the temperature increased to maximum value. Locally, maxima is around maybe 450s. Okay, and remain as a constant for short periods. In this period, actually, we can look at as the burning of the liquid fuel. Okay, here this slide tell you initially the droplet size is almost no change. The preheating process, then they will the droplet diameter will decrease. There is showed some curve line, but still very similar to the linear curve. But when there is a broken point for the time scale, you can see there is a short period finish it, and then you need to wait until this is a 3 second. I'm sorry, this is a very short period, and they will jump to the other combustion mechanism. You can see the temperature start to increase very fast. Okay, but the droplet size they will follow almost a linear curve, and this part actually the rest of the periods represent the burning of the carbon particle. Okay, and there is the gas temperature as a reference, which means you can see the droplet surface for carbon burning. They can return to the very high temperature. That means the carbon particle burning actually on the surface, and the surface temperature will increase to as the flame temperature, because there is the oxidations on the carbon particles. Those kinds of application generally is very interesting, but not too much literature mentioned for the application for the carbon slurry in the industrial furnace. But you should know there is additional application for the multi-component droplet. In this case, the droplet contains a certain solid carbon particle mixed with the liquid fuel. Now we finished the discussions on the droplet combustion, or we may, as I mentioned earlier, actually for droplet itself, in the hot temperature or in the flame surroundings, actually there is no difference for the droplet in the physical process. They still go through the heating and the evaporation. Only they do not care is a hot temperature, hot environment, or very high temperature environment coming from the diffusion flame. And usually people sometimes will simplify our problem. Just look at droplet itself as undergoing the gasification process. That's it. Okay, without consider detailed diffusion flame surrounds in the periphery of your droplet, especially when you go to the spray combustion field. Actually, the droplet do not feel the flame or high temperature. Okay, both of them are the same, and they just the difference is the temperature difference only. Okay. Now we finished the discussion on droplet evaporation and combustion. Now the next part we will go to the spray combustion. We try to bring so many tiny droplets together and to see the overall burning of those bunch of the droplets.